requiring an organ transplant. 11. Patients requiring an organ transplant are tissue typed to match with potential donors. Polymerase chain reaction and gel electrophoresis are used to compare DNA sequences of the patient with those of donors. Gel electrophoresis separates mixtures of DNA fragments according to size. The presence of a specific DNA band indicates that a donor is a suitable match. Patient and potential donor samples were compared with a DNA ladder. The DNA ladder contains fragments of DNA separated by gel electrophoresis which are of known size and measured in base pairs. The distances the DNA fragments travelled were measured and shown in the table. The diagram below shows the result of the gel electrophoresis. So what we've got is quite a nice set of data. So we've got our DNA ladder here with all your different sizes written on, and then we've got the sizes of the fragments for the DNA ladder here and the distance that they travel accordingly. So we've got our smallest fragment is travelling the greatest distance, okay, and then we've got our patient here, which only has one fragment at this point. We have no fragments showing at donor 1. We do have the same fragment as the patient for donor 2, which means they're good as a match. And donor 3, we don't have anything at all. Okay, right, so the gel used for gel electrophoresis contains agarose. Just telling you that. Calculate the mass of agarose required to make 30 centimetres cubed of a 0.8% agarose gel. I think this is a very odd question actually, but okay. So they're asking you to work out mass, and in this case all we're looking for is, okay, if it was a 1% solution, then what we would have is 1 gram in 100 centimetres cubed. Okay, that would be a 1%. So if I've got 30 centimetres cubed, I would need 0.3 grams in 30 centimetres cubed to get a 1% solution. And then I just times that by 0.8 to get me my 0.8% solution, so 0.24. Now you could have done that in one step if you wanted to, but that's how my brain went to work it out. Okay, using information in the table and the diagram, give the distance travelled by fragment X in the DNA ladder. I think this is a total gift. Here is fragment X, 550 base pairs. 550 base pairs travelled 32 millimetres. It is that simple. Okay. On the grid below, draw a line graph to show the distance travelled against the size of the DNA fragment. Okay. You don't always get the line graphs in anymore, so this should be a bit of a gift. Okay, so first of all, so all we're doing is plotting this data. Okay, this data here. So what we want is what we measured going up the side. So this is going to be distance travelled in millimetres. Just lift the entire unit from the, entire heading from the table. And going along the bottom, we're going to have size of DNA fragment in base pairs. Okay, we need to get up to 1,300, starting at 0 because we're starting at 200. So I'm just checking 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. That's a good scale actually. They've been quite nice. Okay, so we take that as 100, 200, 300. Now you're going to do every single check mark. So that's the little things that are coming down. Okay, every single one of them you're going to put something on. Okay, you are not going to miss any of them out. You're going to make sure that you cannot get hit for that as a losing the mark. Okay, now going up the side, we need to get to a maximum of 72. Again, I'm going to start at a 0 in this one. I think that's totally valid. So we're going to get to 72. So let's see, 10, 20, 30, 40, 50, 60, 70, 80. Well, that's just a nice scale again. Every check mark, 40, 50, 60, 70, 80. Yours will look so much neater than mine because the wee scribbly thing doesn't work quite so nicely on that. Okay, so you get 1 mark for that. Okay, taking the exact headings from the table in for your scale and inclusive scale, so everything has to be there, and you have to have used more than half of the graph paper, all of that jazz, all the stuff that you normally have to do. But that gets you 1 mark. Okay, second mark is for the plot and then them being joined neatly. Okay, so you then just have to work your way down. You're like, okay, so at 200 I am looking at 72, so there's my point, At 300, I am looking at 58. Oh, not so easy to do in the computer. There we go. And so on. Because I think you could obviously do this much, much more neatly. 550, be careful, that's on the half box. So make sure that it is on the 550. Okay, midway between the 500 and 600. And again, you're okay for this one. Oh, that's not so neat though. Has to be on the cross point for the 32. The 700 is okay because it's directly on a cross, and your 800 is also nice for that one. Your 1000, I'm now just doing them all when I said I wasn't gonna. There's my 10 and 13. We're looking at 8. Okay, so points must be perfectly put in, and then they must be joined with a ruler, which I can't do on this, but you would do to make sure you get the mark. Okay. Give a conclusion about the suitability of the donors. Already said this when we were just looking at the data set. Donor 2 is suitable. That's it. Donor 1 and 3 are not. Okay. I suppose that's only if we were looking at one fragment to decide, but that's fair enough. The base sequence of a primer used in the PCR procedure is shown below. Give the base sequence of a DNA fragment to which this primer would bind. It's a little bit gifty. I think this is okay. Just remember it's DNA, so we're not going to try and put U's or anything weird like that in. So I'm just looking A to T, U, I said U. Let me just rub that out. A to T, oh, still on the rubber. A to T, T to A, and then we've got a C, and then a T, and then a G, and then a T, 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 and then an A, and then a G, and then a C, and you get the mark. Okay. Complete the table below to show the temperatures used in 2 stages of the PCR procedure and the reason for these temperatures. Okay. So 94 degrees, that's your high temp, and really all we're looking for there is that you're denaturing the DNA strands. Or if we wish to put this in real terms of the bonds, you're breaking the hydrogen bonds between DNA strands. Okay. You need to be precise that you're actually breaking apart the DNA, but it's the DNA strands you're separating. You're not actually smashing up the entire DNA. So just be careful about that. And so maybe the second one's probably more precise and better to use. Okay. We've then got our annealing of primers. So they were accepting anything between 50 to 65 degrees, anything in that range. And question done.